It was the early 1990s, and a man named Vito Bertucci was searching the rivers of the southeastern United States for fossilized shark teeth. At that time, most people knew these rivers occasionally carried fossils from an ancient ocean that once covered the region. Divers would sometimes find small teeth, usually from common prehistoric sharks. But Bertucci kept finding something unusual. The teeth were far larger than anything typically found. Thick, triangular, and serrated, some of them the size of a human palm. And they weren't rare. He kept finding them, again and again. Over time, it became clear these teeth didn't belong to different animals. They belonged to the same kind of animal, a shark far larger than anything alive in the oceans today. That animal is known as the Megalodon. But even with the teeth, it was difficult to imagine the animal itself, because in sharks, almost everything except the teeth is made of cartilage instead of bone. And cartilage doesn't survive long enough to fossilize. So there were no complete skeletons, no full outlines, no direct reference for its actual size, just isolated teeth scattered across different locations. He kept collecting these teeth over the years, dozens, then hundreds, and eventually he tried to understand what they would have looked like together. Using the jaw of a modern great white shark as a reference, he began arranging the fossil teeth into a full reconstruction. Not a model, an actual jaw built from real specimens. And this was the result. Large enough for a person to stand inside, lined with rows of serrated teeth, each one designed for cutting through large animals. By then, the scale of the animal was no longer theoretical. It was visible. And once you see it like that, assembled in real proportions, the question changes. It's no longer, did this animal exist? The evidence is already there. The real question is, what kind of predator was this, and how did it hunt in the oceans of its time? And more importantly, how big was it really? For most of human history, the ocean has been a place we don't fully control. You can stand on a beach, look out at the water, and everything seems calm. But a few meters below the surface, your visibility drops. A few meters more, and you're effectively blind. And in that environment, size becomes invisible. A modern great white shark can reach around 6 meters, or about 20 feet in length. That alone is enough to change how people behave in the water. It's enough to keep people close to shore, enough to make open water feel uncomfortable. Now, scale that up. Estimates suggest Megalodon could reach lengths of 15 to 20 meters, roughly 50 to 65 feet. Some analyses push that ceiling higher. A 2025 study based on fossilized vertebral columns places the largest possible estimate at around 24 meters, close to 80 feet. That's not just larger, that's an animal several times heavier, with a mouth wide enough to engulf large prey in a single bite. The common image is simple, a giant version of a great white, a bigger, more dangerous shark. But that assumption doesn't really hold, because when an animal reaches that scale, it stops behaving like a scaled-up version of something smaller. Everything changes. Its metabolism, its hunting strategy, its role in the ecosystem. And that creates a problem, because we don't have a living reference. No modern predator operates at that exact scale in the same way. No complete fossil skeleton exists to confirm its body structure, and most of what we know comes from teeth. So we're left with fragments, and from those fragments we're trying to reconstruct not just an animal, but an entire way of life. How fast could it swim? What did it actually hunt? Did it rely on ambush or endurance? And what kind of ocean could support something this large? Because an animal like this doesn't just exist on its own. It shapes everything around it. Before we get to the world, we need to understand why we know so little about the animal itself. And the answer is stranger than you'd expect. Sharks are built differently from most large predators. Mammals have bones, dinosaurs had bones, even fish have bones. Sharks instead have cartilage, not just soft cartilage in places, their entire skeleton. Every structural element that holds the body together is made of the same flexible, lightweight material you have in your nose and ears. This was an evolutionary decision made hundreds of millions of years ago, and it worked brilliantly. Cartilage is lighter than bone, which makes a large shark easier to keep buoyant. It's flexible, which helps the body absorb stress during high-force movements. But cartilage has one major flaw. It doesn't fossilize. When a shark dies and sinks, the soft tissue goes first. Muscle, fat, organs, within weeks, gone. But then the cartilage follows. The spine, the jaws, the fins, all of it rots. What survives is only what's hard enough to resist decomposition. The teeth. And here's where it gets interesting. A shark doesn't just have one set of teeth. Over its entire life, Megalodon would have produced roughly 40,000 of them, constantly replacing them row after row, the way modern sharks still do today. Which means everywhere it swam, it left teeth behind, buried in sediment, slowly replaced by minerals, scattered across ocean floors around the world. That's why we have so many teeth and nothing else. And it's also why reconstructing the animal requires inference. Paleontologists use the proportions of modern sharks to estimate body length from tooth size, jaw curvature to estimate mouth width, and bite marks left on fossilized whale bones, deep parallel gouges that match Megalodon tooth spacing to understand how it actually fed. Those bite marks tell us something important. This was not a delicate predator. The bite force estimates for Megalodon sit at around 180,000 newtons at maximum. Let me put that in terms that actually land. A great white shark bites with roughly 18,000 newtons, already enough to cut through bone. Megalodon's bite was estimated to be 10 times stronger. For comparison, if you wanted to experience that kind of force through pressure alone, it would be roughly equivalent to having 3 full-grown African elephants standing on a single point. That force wasn't accidental. It wasn't just a consequence of being large. It was a precision tool. Megalodon's teeth weren't just big. They were serrated along both edges, designed specifically to slice through dense material. When paleontologists examine fossilized whale bones from this period, they find impact fractures and gouge marks, consistent with a predator targeting the ribcage directly. Not biting around a whale, biting through it. This suggests Megalodon wasn't just large enough to hunt big prey. It had specifically evolved to disable large prey as quickly as possible. Which makes sense when you understand the cost of failure, because Megalodon, unlike most modern sharks, appears to have been warm-blooded, or, at minimum, capable of maintaining a higher body temperature than the surrounding water. And warm-blooded predators burn through energy at an extraordinary rate. Estimates suggest that to sustain its body, Megalodon needed to consume roughly 100,000 calories every single day, about 50 times what an adult human burns. Think about what that means for a moment. Every day it didn't eat, it was burning through its reserves. Every hunt that failed had a real cost. And an animal that large, in an ocean that was always changing, could not afford many failures. This single biological fact, that its body demanded constant, massive amounts of food, becomes the thread that eventually unravels the whole story. But here's something most people get wrong about Megalodon. They assume it's a direct ancestor of the great white shark, but if you trace the great white's family tree back far enough, you eventually get to Megalodon. Well, that's not what happened. Megalodon and the great white are about as closely related as a dog and a cat. They share a very distant common ancestor, an early shark lineage that diverged into two separate families tens of millions of years ago. Megalodon belonged to a group called the Odontidae, giant, broad-toothed sharks that grew to enormous size. The great white belongs to the Lamnidae, a different family entirely, which includes mako sharks and salmon sharks. Here's what's interesting about this split. When these two lineages diverged, they made different evolutionary bets. The Odontidae, Megalodon's family, doubled down on size. They became larger and larger, eventually producing the biggest shark that ever lived. They optimized for brute force, for handling the largest prey available. The Lamnidae went the other direction. They stayed relatively smaller, but became faster, more agile, and remarkably efficient hunters. At the time, both strategies worked, but one of them had a longer shelf life. Megalodon first appears in the fossil record around 23 million years ago, a time when the world's oceans were warmer, shallower in places, and rich with large marine life. Crucially, this was the age before large baleen whales. Early whales, the ancestors of modern humpbacks and blue whales, were actually small by today's standards. They were mostly toothed, quick-moving, and spread across relatively shallow coastal waters. And Megalodon sat at the top of this entire system. It hunted early whale species, it hunted large fish, it likely controlled the population dynamics of everything below it in the food chain, the way large apex predators always do. For roughly 13 million years, this arrangement held. 13 million years. For context, our entire genus, all of human evolution from our earliest ancestors, spans only about 3 million years. Megalodon as a species outlasted that by 4 times over. It was not a brief experiment. It was one of the most successful apex predators in the history of life on Earth. Around 5 to 6 million years ago, things began to shift. Not a single catastrophe. A slow tightening, one factor at a time, until the combination became impossible to survive. The first thing that changed was the climate. The planet began to cool, and as it cooled, the oceans responded. Warm, shallow seas that had covered large parts of the continents began to pull back. Coastal waters, rich, productive, full of large prey, started to shrink. And at the same time, something was happening to the whales. Faced with less food and more competition, a group of early whales made an unexpected evolutionary shift. They gave up their teeth. Instead of hunting individual animals, they evolved baleen, long, fibrous plates that act like filters. Now, instead of chasing a single seal, they could swim open-mouthed through clouds of krill and tiny fish, straining enormous quantities of food in a single pass. It sounds simple, but the logic behind it is powerful. Hunting is expensive. Every step in the food chain costs energy. A seal eats fish, the fish eats smaller fish. By the time that energy reaches the seal, most of it is already gone. These whales skipped the middleman entirely. They went straight to the base of the food chain. More food, less effort. And so they grew, and kept growing. With unlimited food and no predator capable of stopping them, there was no biological reason not to. But here's what gets interesting. For decades, every reconstruction of Megalodon assumed a great white body plan, the stocky, barrel-chested shape people know from documentaries and movies. But that same 2025 study that pushed the size estimate to 24 meters also looked at something else. When researchers compared Megalodon's vertebral proportions to over 100 living and extinct shark species, the closest match wasn't the great white at all. It was the lemon shark, a longer, more slender animal with an elongated body. Megalodon wasn't built like a great white. It was built like a giant cruiser, long, streamlined, designed to move efficiently through warm, open water. Its cruising speed, estimated from fossilized scale analysis, was only about 2 to 3 kilometers per hour, no faster than a modern great white, despite being several times larger. This was an animal built for slow, energy-efficient patrolling with short bursts of explosive force when it struck. While Megalodon's prey base was changing, while the warm water whale species it relied on were either disappearing or transforming into enormous filter feeders far beyond its reach, another predator was quietly getting better at exploiting the gap: the ancestors of the great white shark. Built for colder, deeper water in a way Megalodon simply wasn't, they could pursue agile prey through environments a 15-meter shark couldn't follow. And early baleen whales, still relatively small at this point, before millions of years of unchecked growth, were well within their range. What was happening, in effect, was a handover. The prey that had sustained Megalodon was gradually shifting, either disappearing or transforming into something too large and too deep for Megalodon to reach. And into that gap, the great white's ancestors stepped in. Smaller animals, filling the space more efficiently than Megalodon ever could. And Megalodon, with its enormous body burning through calories every single day, couldn't afford to wait out the transition. This is why some researchers describe the great white as an indirect cause of Megalodon's extinction, not direct competition. They weren't fighting each other for the same meal on the same day. But while Megalodon was built for an ocean that was disappearing, the great white lineage was quietly adapting to the one that was arriving. And in the end, that distinction was everything. There's one question that always comes up: is it still out there? It's worth taking seriously because the instinct behind it isn't crazy. In 1938, a fishing trawler off South Africa pulled up a fish that scientists had believed went extinct with the dinosaurs, a coelacanth, alive, undiscovered for 66 million years. So the logic makes sense. If that's possible, why not Megalodon? See, Megalodon shed roughly 40,000 teeth over its lifetime. In every ocean it ever swam through, it left them behind. We find them on seafloors all over the world, and the most recent ones date to exactly 3.6 million years ago. Not 1 million, not recently. Modern whales, which would be the obvious prey for a 60-foot shark, show no bite marks consistent with Megalodon. None. And the coelacanth survived because it lives in deep water caves, barely moves, and needs almost no food. Megalodon was the opposite of that in every possible way. But here's what that actually means, because the extinction of Megalodon didn't just remove a predator from the ocean, it changed what the ocean could become. For as long as Megalodon existed, baleen whales had a ceiling. Juveniles needed to stay small, fast, and hard to catch just to survive long enough to reach adulthood. The moment that pressure disappeared, the moment Megalodon was gone, the ceiling lifted. Unlimited food at the base of the food chain. No predator capable of taking adults. Millions of years of open ocean. So they grew. The blue whale, 30 meters long, the largest animal ever known to have lived on Earth, didn't exist when Megalodon was alive. It couldn't have. It took Megalodon's extinction to make room for the largest creature in the history of life on this planet. That's the thing about apex predators. Their presence defines the ecosystem they inhabit, but so does their absence. Megalodon didn't just live in its ocean, it shaped it. And somewhere out there right now, a tooth that once sat inside a living Megalodon is resting on a seafloor, waiting to be found.